Hi class, in previous video we were talking about binary trees, and just it's important to understand that tree data structure has different types of trees, and we are focusing on binary trees. Binary trees, it's when the parent or root cannot have more than two children. And if you take a look, each parent has two or less children. So it's impossible to have three children of a root. That's what binary tree is. Now, what you need to understand, and you will see it later on, that binary trees have different type of binary trees. What I mean, there are different types. For example, binary search tree, AVL tree, and so on. So today we are going to talk about binary search trees, which is type of binary tree. And in next video, next week, we are going to talk about AVL tree, which is another type of binary tree. But for today, it's binary search tree. And usually we call it BST. So binary search tree or BST is a binary tree that is either empty, which is null, or, yes, remember binary tree can be empty, right? Any tree can be empty, but it's still binary search tree. Or a root node are such that every element of R's left subtree contains data less than R's data. And what it means, left child is always less than its parent, always. And you can see it here. 29 is less than its parent. It's less than 55. And the same is here. -3 is less than 29. It's always less than its parent. And same as here, 60 is less than its parent. So it's a rule, it's must-have of binary search tree. If it's violated, it means it's not a binary search tree. Probably it's some other tree, or probably it is some other binary tree, yeah, or just tree in general. So again, binary search tree, what it makes unique, the left child is always less than its parent. But that's not it. Each right child is always greater than its parent. And we can see it here. 87 is greater than 55. Or 91, which is a right child of 87. So 91 is greater than 87. And same as here, 42 is greater than its parent. So again, what we need to remember, each left child is less than its parent, and each right child is always greater than its parent. So, and it's true for all of the nodes, for all elements. So it is very important to understand. That's what it makes a binary search tree. So BSTs store their elements in sorted order, which is helpful for searching and sorting tasks. And that's why we call it a binary search tree, because we already kind of have an idea what located where and so on, because it's already sorted, have some sorted order. Let's take a look at some exercises here. So which one of the trees shown are legal binary search trees? So do you remember property of binary search trees? Let's see. So here, as you noticed, binary search tree can hold any data type. Here we have chars. Of course, it can be strings. We can see double here. We can see negative integers, but still integers, right? And integers again. So let's start with this tree. We have M here and its children, G and Q. So G is less than M, so nothing here is violated. Okay, we are good here. So B is less than G, which is also good. And E is greater than B, which is also good. So this part is okay. Let's see here. Q is larger or greater than M, so we are good here. K is less than Q, and X is greater than Q. So this is legal binary tree, which is good. And you can notice actually all the elements in left subtree are less than root. And it cannot be violated either. It's very important. And the same is here. All the elements of right subtree is greater than root. So next tree is just one node, 42. Is it legal? Yes. It's still a tree, just with one node. Remember, it can be even empty, which means there are none nodes. So next tree is a tree of integers. Let's see. It has a root 8, which has two children, 5 and 11. 5 is less than 8, 11 is greater than 8, so we are good here. So 5 is greater than 2 and it's less than 7. So perfect, that's what we want. And 2 is greater than 4 or less than 4, so we are good here too. Let's take a look at the right subtree. 10 is less than 11, which is good. 18 is greater than 11, which is good. And then we have 20, which is greater than 18, which is good. But here we also can have 18. So it is not legal to have duplicates in binary tree, in binary search tree, because all the elements, they are unique. So this is not a legal tree, no, just because of this. Let's see, let's take a look at this tree, which is -5 as a root, -1 and -7. So obviously -1 is greater than -5 and -7 is less than -5. So it is violated. It is not a legal binary search tree. So this is not a BST. Because remember, left child is always less than its parent, and right child is always greater than parent. And here we can see another tree of doubles. 7.2 is a root, and it has two children, 1.9 and 9.6. 1.9 is less than its parent, which is good, and 9.6 is greater than its parent, which is good. Also, we have, it has two children, 8.1 and 21.3. 8 is less than 9 and 21 is greater than 9. So this is good tree. This is legal. Let's write a method to, let me see. Yeah, let's take a look at slides first. So the main idea of binary search tree is that it's easy to search for some values. Searching in a BST always starts at the root. We compare a data stored at the root with the key we are searching for. Let us call target, and you remember some methods with target. We already did some search, some binary search or sequential search. And this is different because it's search in binary tree data structure. So if the node does not contain the key, we proceed either to the left or to the right child, depending upon comparison. So we have a method here, which is, in this example, it takes integer x or target as a parameter and, of course, our root. So if root equals null, return false. If target equals root.value, return true. But we need to keep going. So that's why we have this if statement. If target less than root.value, go to the left side of the tree. You understand why is it left side of the tree? Because everything in order in binary search tree. Whatever is less, it's left side, right? Whatever is greater than parent is in the right side. So if target is less than root.value, we continue with left subtree recursively. Else we continue with right subtree. So if the target is smaller, we go to the left child, otherwise to the right child. The recursive structure of binary search tree yields a recursive algorithm. Just like I told you before, binary trees are perfect for recursion. Just look at binary tree. It's like pure recursion. Very easy to implement. Couple lines of the code. So how do we search? Okay, into some exercise. And what we just saw, we compare target. For example, our target is 4, and we compare it with, I will show you. We compare it with root.value. And what is root.value? It's each node, right? It depends on where we are. So first, for example, our target is 4. It's here. We start at the root and we compare target, if target less to the root.value. So 4 is less than 18. Yes, that's true. So go to the left subtree, somewhere here. Now it compares 12 with 4, and if 4 is less, go to this. And of course, it's also compare root.value with target. That's how we return true. And it's here. If x equals root.value, return true. So that's how it works. So how do we insert into binary search tree? How do we add new values? new elements. The insertion procedure is quite similar to searching. Why? Because we need to see, because it's in order, we need to see where to insert it. We start at the root and recursively go down the tree, searching for a location in a binary search tree to insert a new node. If the element to be inserted is already in the tree, we are done. We do not insert duplicates. The new node will always replace a null reference. So let's say we want to insert 7 here. We compare 8, which is root, with value we want to insert. So if 7 less than 8, true, go to the right, to the left side. Is 7 greater than 3? True, go to the right side. So is 7 less or greater than 5? So it's greater. So it goes right here and you can see it here. So it's like a searching, we compare each time. And this is very important to understand because that's how you code it. Let's have some practice with adding nodes to BST. Suppose we want to add the value 14 to the BST below. Where should the new node be added? So again, we start at the root, we compare 8 and 14. We know 14 is greater, so we go to the right side, to the right subtree. We compare 11 and 14. 14 is greater, so we go to the right subtree. We compare 14 and 18. 18 is less, so we go to the left subtree. And it is empty, there's nothing, the spot is available, so we insert it right here to the left, child of 18. So what about value 3? We compare 8 and 3, 3 is less. We compare 5 with 3, 3 is less. We go to the left side again. We compare 3 and 2, and 3 is greater, so we go to the right subtree. We compare 3 and 4, 3 is less, so we go to the left subtree, and we insert it here as left child of 4. What about 7? Actually, those 3 questions, two questions. Actually, I will leave it for your practice. Now let's construct a binary search tree from the scratch, and you have to understand how to do it. You have to be able to do it. I'm going to ask it on the quiz or exam or even final exam. So must know, pay attention. Given a sequence of numbers 11, 6, 8, 19 and so on, draw a binary search tree by inserting the above numbers from left to the right. So we start with empty tree and we need to insert 11 first. So this is 11 here. Sorry, it's very difficult to draw here. Okay, 11. No, let's do here. So this is 11. It is our root. Now we need to insert number 6. So how do we insert it? Where do we insert it? We need to compare 11 with 6, and if 6 is smaller, we insert it to the left subtree here. So now we are going to insert number 8. Is 8 less than 11? True. So it's going to be left subtree. Now we need to compare 8 and 6 to see where it goes. Is 6 less or greater than 8? 6 is less, which means 8 is greater. So it goes to the right subtree here. So now we are going to insert 19. 19 is less or greater than 11. It's greater, so it goes to the right. Oops, it goes to the right subtree here. Okay, I have some tree here. I tried to hide it, but sorry. Okay, 19. Now we are going to insert 4. Let's see where it goes. So 4 is less than 11 and 4 is less than 6. So it goes right here. Now we are going to insert 10. So 10 is less than 11, so it's going to be left subtree. 10 is larger or greater than 6, so it's going to right subtree. 10 is greater than 8, so it's right subtree again. So 10 goes here. Okay, now we are going to insert 5. 5 is less than 11, 5 is less than 6, but 5 is greater than 4. So we insert it right here. This is 5. So now we are going to insert 17. 17 is greater than 11, so it goes to the right subtree. But 17 is less than 19, so it goes to the left subtree of 19. So it goes right here. Now we are going to insert 43. 43 is greater than 11 and it's greater than 19. So it goes right here. 43. Sorry guys for this mess, but it's complicated. So now we are going to insert 49. 49 is greater than 11 and it's greater than 18 and it's greater than 43, so it's going to be right subtree of 43. 49 is going to be here. Now we are going to insert 31. 31 is greater than 11, it's greater than 19, but it's less than 43. So it goes to the left oh sorry, 31. So it goes to the left child of 43. That's what we got. Sorry, it's a little bit ugly, but I can show you the better one. Hold on. One second. Okay, that's our tree. That's what we just did. So again, you start with a root. You add 11, it's going to be a root, and then you compare next element to see where it goes. If it's less than root, it's going to be left subtree. If it's greater, it's going to be right subtree, because you see everything, every left child is less than parent, and every right child is greater than parent. Now let's see how we can remove nodes from the tree. So there are three different cases. And first case, when you want to delete a node with no children. So it's very easy. You simply remove the node from the tree and that's it, because it doesn't have any children and you don't need to rearrange anything. So here's an example. Let's say I want to remove 18. So I just remove it and that's it. And here is my new tree. Again, this case only works when the node which you want to remove doesn't have any children. So you just remove it and that's it. Case number 2 would be when you want to delete a node that has one child. So you need to remove this node and replace it with its child. It's also pretty much simple. Let's say we want to remove 25 here, and we can see it has just one child, which is 30. So we remove this node and we replace this node with its child. So it goes here. And you can see here result. So it was 25 with a child 30, now just 30. So again, when you want to delete a node that has just one child, you remove this node and replace it with its child. Pretty much straightforward. And finally, last case. The node you want to remove has two children. So how do we remove it? You remove the node and replace it with the largest node in its left subtree. So let's say we want to remove this node, which is 20. And we want to replace it with, so it has right subtree and it has left subtree. What you need to do first, you need to find a largest node in left subtree. So we have 16, 18 and 19. 19 is the largest. So you take this node and you replace it. You remove 20 and you place the largest node of left subtree on a place of 20. And that's what we get here. We had 20 here, but now we have 19. Let's write a program for binary search tree with methods that we just learned. Before we start, remember I need bnode class, I need my node object when I work with nodes. we have done it with linked list, and now binary trees, it's also nodes. So please always use this class, otherwise it's not going to work. And just a reminder, I have a value here, and actually I'm going to use integer now because I want my tree to be filled with integers. And I have bnode left and right, which is links to the left and right child of the node. And I have two simple constructors, just regular ones. I'm not going to change anything here. No, actually I am. I'm going to change integer value and integer value. Let's start. I'm going to create public class, and I'm going to name it BST, which is binary search tree. And I'm going to have bnode root, and of course constructor public BST, it's name of my class, and root is null. That's my constructor here. Let's write a method that will add new elements to our binary search tree. I'm going to write a private method. And I hope by now you understand why it's private, because I have bnode root that I'm going to use as a parameter, and I do not want this root to be in my main method when I'm testing my program. So I'm going to, okay, private bnode. It's going to return new root of your tree. So bnode, and name of the method is add, and it will take integer x as a parameter. That's the value I want to insert in my binary search tree. And of course bnode root, which is a root of my tree. So if root equals null, return new bnode with parameter x. So if it's null, we just inserted there our x, our value to be inserted. But if it's not null, then we need to see where we're going to insert it. You remember we have left subtree and right subtree, left child and right child. And left is when the value or child is greater than parent, and it's very important to remember. So if x less than root.value, you remember when I showed to you examples how to insert, we were comparing value to be inserted with nodes. That's exactly what we are doing here in the code. So our root at left, and we are doing it recursively. You remember I was telling you that binary search trees, or actually any binary trees, are natural for recursion. So parameter x, and we have parameter root here, but of course it's going to be root.left. So basically what we just did it is if the nodes, oops, if the node's value is lower than the current node, we go to the left child. And this is what it happens. We compare and then we add it there and replace. There is another case which I will call else, meaning if x greater than root that value, go to the right child. So else will be basically opposite of this. So if the node's value is greater, then the current node will go to the right child. Since we have else statement, we do not repeat if statement, right? We just else. Okay, root right equals add parameter x and parameter root dot right this time. In case x is greater than root dot value, we call this method with parameter x and root dot right, because we need to go to the right. Remember, it's recursion. Okay. And of course, we need to return root. Return root. And that's our method, but we are not done because we still need our public method. I'm going to do Boolean because I want to see if it was added successfully or not. It's going to take integer value as a parameter, and I would say my root is add value, so parameters of my private method, right, which is value and root. And I'm going to return true. It's not necessary, it can be still void or anything else you wish to do. I just decided to do Boolean. I think your book has Boolean, yeah. Okay. So let's write a next method, which contains. I told you before that binary search tree is just great for searching for elements. So let's write this method. So it will take, okay, let's do it private also. And it's Boolean because it's going to return true if the element is found and false otherwise. Contains, its name of the method, which is going to take parameter integer x and bnode root. Integer x, it is a target which you are going to look for. You can name it target, it doesn't matter. So if root equals null, we return false. Nothing is there. And if root, so you understand that root is your current node, right? Okay. If x equals root dot value, what does it mean? We return true because it is found, right? X our target and root value, our value of our current node. And we have a couple more cases. If x less than root that value, you remember it's binary tree. We always need to go to the right or to the left to be able to traverse the entire tree. So we always need to compare. We always need to determine where to go. So if x less than root that value, we continue going there. Return contains with parameter x and root that left. And else, it means if x greater than root that value, we go to the right subtree. So else return contains with parameter x root that right. And that's our method. Of course, we also need public method, which is public boolean contains with parameter integer x. It's our target which we want to look for. And I just return and call this method, this private method, which is contains with parameter x and contains with parameter x and
I didn't get that.
And it's our public method. So when we call our method, this method from the main, we call this method, right? We just need one parameter. That's why. Okay, it was contains method. And now let's write a method size to check the size of our tree. It's also going to be private integer size. Why integer? Because it will return how many nodes your tree has. And it's going to be bnode root as a parameter. And now we have if statement. If root is null, we return 0, not 9, 0. And else we return 1 plus. You remember in recursion 1 plus is your counter. That's how you count anything in recursion. Sorry. So return 1 plus size, which is name of the method, with parameters, and it has just one parameter, root. But remember, it has two subtrees always. So we need root.left plus name of the method, because this guy will return only number of nodes in your left subtree. But what about right subtree? We need to calculate it also. Right. And it's just size. It's not height or anything. It's just how many nodes in your binary tree. Okay. So this is a method. Compile. Okay, now let's create a tester to test our methods. Public class BS3 tester, that's how I'm going to name it. Public static void main, just main method. String args. I'm going to create my tree, is here, tree. I'm going to name it tree, my object. New BS3. Okay, now let's test it. Actually, first let's write one more method. I think I forgot about this. Okay. Just what we did with linked list. I'm going to write a method to see if the tree is empty or not. Public boolean is empty. Return root equals null. That's how I know if my root is null, it means my tree is empty. Okay, now let's see if it's empty. System out println is empty. So tree, name of my object of my tree, and name of the method. Compile, run, and is empty, true. Now let's add some values, some elements to my tree. Tree, add. Actually, you can, okay, you can do system out println. Yeah, let's do it. System out println tree add, and I'm going to add 1. Compile, run, true. So here, if you remember, I created my method to be boolean. In case to see if it was successfully added or not. So let's see, is added, true. So I just added 1 to my tree. Now I'm going to add, but let's do it without boolean. Just tree, name of the method, and parameter which you want to add. Let's say it's 1, 10, 14, 15, 7, 7, and I think that's enough. 2. Now let's check if it's empty after I add elements. Compile, run, is empty, false. So that's what I added to my tree, and now it has those elements 1, 10, 14, and so on. Let's check if it contains, let's say, 14. And now let's check if it contains 12. Compile. Contains. Let me check what's wrong. Contains, I misspelled. Compile, run. Contains 14, true. Contains 12, false. So that's how contains method work. What else? Let's see what size of the tree. Size, tree, and name of the method is size with no parameters. Let me check. Okay, I will write here public. I forgot about public. Public int size without any arguments. So return method size with parameter root. Compile, run, and 6. Let's see, 1, 2, 3, 4, 5, 6. If I remove something, it's just 3. So again, it's recursion, and it requires some practice, but it's not that difficult because it's almost always the same. You need to just your base case, and then you need to determine which side you want to go. Based on what? Based on comparison. Remember that right child of a parent is always larger than parent, and left child is always less than parent. So that's what you need to remember in order to keep going to the entire tree. I mean, if you want to search for something, or if you want to add something to your tree, or I can ask you to remove, or not to remove, I can ask you to, let's see my slides. I can ask you to find minimum of your tree or maximum. How would you do this? You know where's the minimum. Minimum is always the most right node or the most left node. And you can see it here, right? It would be the minimum. And what about maximum? Maximum is always located at the very left, or it's the very right place. The most right node of the tree. So basically, recursively, you would just go all the way to the left. The last left, oh, sorry, it's right. The most right node is the largest. The most left node of your tree is the smallest. But you know how to do it recursively, so you call the method and you go to the left. I think it's a better example. You go all the way to the left, or you go all the way to the right, and you can see it's everywhere like this. Okay, let me know if you have any questions. I will be happy to help you. So just don't be shy.